minus 1. This simplification is seriously orgasmic. Don't you agree? This is f***ing amazing.
Papa Flammy's Advent Calendar.
Here.
Good morning, fellow mathematicians. Welcome back to another video. I just now grabbed a fresh new piece of chalk because we are going to need the whole one for today. We are going to defeat the final boss of this year's Advent Calendar. No, it's not beneath first formula for log gamma. This one is easy in comparison to what we are going to do today. It's just one simple woodworking problem that we are going to cover. An engineering problem. I have spoiled it a tiny little bit before when I traveled back from Italy. It took me a bunch of hours to figure it out completely, and I already made a few prerequisite videos on this topic. Links down there in the description. It's going to be amazing and you're going to love it. But before we dive into the main video, don't forget to check out the illegitimate child of myself and Elon Musk, the Cyber Tensegrity. It's a new release over on stemage.eu. Various different wood types available. Check it out. Link down there in the description too. Now, before we can get into today's video, you should definitely also make sure to check out Flammy's wood video, okay, over on my woodworking channel, because without this you're going to be a bit lost, because you won't know what the contraption is going to look like that we are dealing with today and the mathematics behind it. So make sure to check it out and then please come back. Other than that, for those of you who have already watched it, we are dealing with a router table. A router table is a spinny thing where you can push your wood along and you can route it. Okay, this is what a router table does. But my router table is rather special because it's dealing with basically a fence which is pivoting around one point. Okay, it's going to spin in circles basically. Okay, the regular fence that you get for router tables, you can just bring it upwards and downwards, slide it basically on T-tracks. But mine is a bit different. You're going to rotate it. And if you take a look at the contraption, you can find a picture here. You're going to notice that it's going to look like this approximately. So if we have a fence which is not rotated yet, it's going to look like this. Okay, so we are going to have this part in the middle, okay, which is kind of open. This is where our router bit is going to lie. We are just going to say that our router bit has no dimension at the moment. We are going to mention how you can calculate it with a router bit in it at the very end. It's going to take a while, but other than that, this is basically what it looks like. And we already know a bunch of things about our router table. For example, how wide is our router table? The only thing that we really care about is half the width of the router table. We're going to call this distance to the router bit r. Also what we know is where our pivot point is. Our pivot point lies, for example, right in the middle of our whole fence, okay? Or it could be at the end of the fence or at the start of the fence. Really doesn't matter, but we know where the point lies. We can measure it using basically our ruler, meaning we're going to call this distance right here m. Those are the things that we know about at the moment. But now, what happens if we were to rotate our fence around a tiny little bit? What is going to happen is this very situation. Now it's going to be rotated. It's gotta look like this. And obviously our router bit is going to stay at the position where it was originally. And all we did is we rotated it upwards. So this distance r is still the same. We also have this distance m being still the same. But now we have a tiny little problem. Namely, we have rotated it by a certain angle. Let's call this angle phi. This is the one that is really interesting to us today. And based on our angle phi that we are going to rotate it around, we are going to measure our distance between our fence. Okay, our distance lies perpendicular on our fence and our router bit. This is the distance that we are interested in. We want to push a block of wood through, meaning we want to measure, for example, where the groove is going to go after a rotation of 5 degrees, or the other way around. If you have the degrees given, how can you measure, for example, the radius that we have right here, or the distance between our fence and the router bit? And this is the problem we are going to deal with today. We want to find a function phi, for example, our angle rotated by, with respect to our distance that we have between our fence and our router bit, or the other way around. Really doesn't matter. It's an implicit function at the very end. And this is the main problem we are going to be dealing with. And now we are going to dive right in. And we are going to turn this whole problem into, let's say, 3 stages. We are going to go through 3 stages of grief here. The first one is accepting the fact that we are engineers now. No, we are doing mathematics, strict mathematics. So the first thing we are going to do is we are going to turn this into an analytic geometry problem. We want to find out all the functions that correspond to our router fence that we got right here, our router table fence. The next stage is going to be to find the distance between our fence and our router bit. After we have done this, the last thing we need to do is we need to find our, well, function, okay, phi with respect to r and all the other variables that we got. Those are the three stages that we are going to go through, and let's go ahead and get started with the first one. Now the great thing about this system is that we are not dealing with weird functions or shit like, I don't know, curvilinear coordinates or three-dimensional system. It's actually just rotating linear functions, which is pretty good. That is rather easy to express using trigonometric functions at the very end. So at first we are going to define ourselves a function which is going to pivot all the time around a certain point. We know what our pivot point is. Our pivot point is where our m is going to lie. We are going to just use linear function for that. Okay, we are going to make it dotted and we are going to call this function f. Let's put it into a coordinate system. Now what would be the best position for such a function which is going to pivot around a point at all times? Well, obviously 0, 0, because we don't have a y-intercept which is going to change in the process at all times. Meaning we are going to let it go through 0, 0. This right here is our function f. Now, another cool thing about our system is that we can easily define our front of our router fence to be a parallel function, parallel obviously to our pivoting function. We're going to call this function g, and it's going to be parallel at all times to our function f. F parallel to g, and it's going to look like this. And those are the two functions we want to express at first using some kind of rule. So let us go about the function f at first. Our function f of x obviously doesn't have a y-intercept, meaning it's of the form slope times our x values that we put in here. And how can you express a slope? Well, obviously using the slope triangle. If we take a look at this function, okay, it goes through here, and then we have our slope triangle here. Our slope triangle has the nice property that we can also express it using a certain angle phi, the rotational angle. This is the angle we are interested in. For the very end of the video, we are going to call it phi, and it lies here. It's basically just the amount of rotation between the x-axis and our linear function f. Now, if we put our right hand run into here, you also notice that delta x and delta y lie here, and that means that delta y divided by delta x is the same as, well, that's the right triangle that we got here. It's a slope triangle after all, meaning opposite divided by the adjacent is going to be the same as the tangent of phi. Okay, so meaning our function f of x, this is just basic linear functions, can be expressed as the tangent of phi times our x values. Okay, thus far that's good. How about the function g of x? Well, g of x is parallel to our function f at all times. If it's parallel to this function, obviously it's bound to have the same slope as the function f, meaning we are already done with the slope part. So that's tangent of phi times x plus some, well, y-intercept. We are going to call it b. And now take a look at this. When our fence is going to be rotated, this also means that our y-intercept is going to change all the time. Just take a look at this. Okay, if I rotate my arm, if it's in this position and I rotate it downwards, okay, it's going to stay parallel to our f at all times. Our y-intercept is going to change all the time. It's going to rotate upwards or downwards depending on the angle that we are taking. Meaning we need to define our b that we got right here somehow in terms of the angle phi that we just introduced. Now that's a bit more complicated, but still not too hard, to be honest. Now if we take a look at our y-intercept, okay, we're going to call it b. It's going to lie in a negative direction in some way. Okay, it's going to be negative b, so this is just for later. But how can we define it using the angle phi? Our angle phi lies up here. And what we got here is a right triangle. We could make use of this one, but that's not a good idea because we have not much information about g at the moment, meaning we can't make use of the 0 that we got here. But we have a different piece of information that we can use. Namely, what happens if we put a perpendicular on our g which goes right through the origin? This perpendicular, take a look at that. Our origin is the pivoting point. this is our distance m that we got here, obviously. Now meaning, this right here is our m. If we enhance this picture a tiny little bit, just making it a tiny little bit bigger. Okay, this right here is our coordinate system. And now we got this situation. This right here is m, this right here is phi, and this right here is b. We can actually start to make use of, well, right triangle properties once again. This right here is a right triangle. As I said before, it's a perpendicular lying on our G. Now, all we really need to get ourselves something with respect to phi, which also includes our y-intercept b. We need to put the angle phi into here somehow. But this is very easy. Just take a look at that. Now, since this right here is a perpendicular on our function g, it's also going to be a perpendicular on our function f, since f and g are parallel at all times. Meaning phi plus some angle alpha, let's call it alpha here, are going to make up 90 degrees. Okay, so phi plus alpha is equal to pi over 2. Now, do you know what also is 90 degrees? Our coordinate system, okay? When those two axes met or meet. Meaning overall, this right here is also 90 degrees, what we got here. But 90 degrees is composed of alpha plus phi. Meaning what we got here is actually nothing other than our angle phi once again. Meaning we got a nice triangle going at this point. This triangle being, this right here is the right triangle, this is m, this right here is phi, and this right here is b. Now, we can take a look at just trigonometric functions, obviously. We know this right here has to be the cosine in some way, because we have the adjacent and we have the hypotenuse. Meaning m divided by b is nothing other than the cosine of phi. Meaning if we were to solve all of this for b, we are going to get that g of x is nothing else than tangent of phi times x minus, and now we get m divided by the cosine of phi. This right here is our function g of x. Now we have defined 2 of 3 functions that we still need. So what is the third function that we are going to need? If you look closely, what we want to find out at the very end is the distance between our fence and our router bit. Meaning the third function that we need to introduce is a function which goes through our router bit, and then if we find the intersection point of our function g of x and this new function, let's call it capital D, and the position where our router bit is, this right here is going to tell us what the distance is actually going to be, and this one we can express using the angle phi or something. Now, we need to introduce now another function, let's call it D. Let's put our router bit point here, okay? This is one point of reference which is extremely important for this problem. And we already found out what the coordinates of this router point are going to be. Now what are the coordinates of this point? The coordinates of this point are going to be, okay, so if we take a look at the original position, then it obviously lies in our coordinate system at negative m as our y value and r as our x value. This is where our point is going to lie. This point of reference is going to be very important for the very end, so keep this in mind for the distance function. But other than that, it's also going to help us to find out what our new function d of x is going to be. Now our new function d of x, how does it need to lie in the coordinate system? Well, it does need to be perpendicular to our function g, because we want to find out the distance between the fence and our router bit. And the shortest distance between 2 points is a straight line, obviously. And it's always the case if we have, for example, such a fence, and then the distance is always going to lie perpendicular as the shortest distance on our fence too. This is just something that you need to take into consideration. Okay, otherwise, if we, for example, say that our function d lies like this, obviously this is not going to be the distance between the router bit and the fence. I mean, it's pretty easy to see. I hope you can see this too. Now meaning, if we have this other function now, it's going to lie like this in our coordinate system, where our function d is perpendicular to our function x, g that we got. Okay, so now this right here is our function d, and we need to define it once again. Now what is d of x? D of x is of the form ax plus b. It's a linear function once again, and it needs to lie perpendicular on g. Perpendicular means that what we basically do with our angle phi, so if t runs like this, phi perpendicular means 90 degrees, we are going to rotate it by 90 degrees overall. That's a very easy relationship that we got here, but we are going to still formalize it a tiny little bit. So meaning the slope a of d of x is going to be the same as the tangent of phi plus pi over 2, because we are going to rotate the function by 90 degrees. Okay, now this is very easy to solve, okay, because we know what the tangent is. It's nothing other than the sine of phi plus pi over 2 divided by the cosine of phi plus pi over 2. Okay, now sine plus phi over 2, moving it to the left, is going to give us negative the cosine of phi, and the cosine, moving it a tiny little bit more by pi over 2, is going to give us the sine of phi. Meaning overall this here is nothing other than negative the cotangent of phi. That's a very easy relationship. If we have two functions and one is perpendicular to the other, linear functions at that, then if the slope of the first function is going to be, for example, m, then the slope of the perpendicular function must be negative 1 over m, negative 1 over the tangent of phi. That's a very easy relationship which is going to hold for all linear functions. Meaning our d of x at this point is negative the cotangent of phi times x plus our y-intercept that we do not know at the moment. But we are going to find it out. It's actually rather easy. And for this we are going to enhance our coordinate system once again a little bit more. Now this right here is our function d. Our function d, please remember this, is going to run through our router bit in some kind of way. Meaning what we know is that this distance right here is r, and this distance in the y direction, negative down here, is going to be m, obviously, once again. Just take a look at this sketch. So this right here is m. But to fully define our y-intercept, which is going to lie up here, we still need to know how much it must lie over our y-axis, over our x-axis. Meaning we are going to call this distance right here, yeah, I don't know, let's say our y-intercept is b. Yeah, this is what we called it before. Now, we want to define it using our angle phi once again. Please remember that our angle phi was like this at first. This right here is our angle phi. And now you can go through the same arguments as before, as we did down here, but it's not going to change too much. Okay, it's basically the same argument once again. What you're going to find out is that this angle up here is once again phi. Okay, nothing is going to change here. It's very easy to prove. I'm not going to go through the process once again. Just use some of the interior angles with this phi that you got right here, and then you are basically going to be done in no time at all. Okay, so you can already see it. If you just take this triangle and you are going to rotate it and put it on here, you're going to see that this right here is the projection of this angle phi once again in our triangle. Meaning what we got overall is that we have some kind of right triangle going on here, and this right triangle is once again being defined by the tangent. Namely, we got that r divided by b plus m is going to be the same as the tangent of phi. Okay, opposite divided by adjacent. And now we can take the reciprocal on both sides under the condition that it's not equal to 0. Okay, we are going to assume it's not. You can go through the analysis of the angle and everything here. But overall, we are going to get that b plus m divided by r is equal to the cotangent of phi. And now we want to solve all of this for our y-intercept. Multiplying both sides by r, it's not equal to 0, obviously not. If it were the case, then we wouldn't have any router fence at all. We are going to subtract m on both sides, meaning b is nothing other than r times the cotangent of phi minus m. Whew, that's a mouthful. Meaning d of x, our third function that we were striving for, is now negative the cotangent of phi times x plus r times the cotangent of phi minus m. And now we are done with the first step. Now on to the next one. Phase number 2, part 1. We are going to find the intersection point between our two most important functions now, g of x and d of x. Looking at the graph once again, the intersection point is obviously where those two meet. And how do you find the intersection of two functions? Well, graphically and also algebraically, it's going to happen by setting both of those equal. Meaning if we were to do so, and also we need to find the x value obviously and the y value then together also as a certain point. And we're going to call this point xi and yi. Now, if we were to set those two equal, it's just plain old putting everything in it first, substituting, meaning we're going to get, and now for simplification purposes, it's going to make our life easier. I'm going to leave out the phi at all times, and I'm going to express all the tangent, cotangent, etc. with respect to their sine and cosine definitions. Meaning tangent of phi is hence sine divided by the cosine times x, and then minus m divided by the cosine is equal to negative cotangent is cosine divided by sine, so cosine divided by sine times x, and then plus r cosine divided by the sine times r minus m. And now we are going to go through a whole lot of manipulations such that we arrive at some kind of nice expression. Okay, it takes a bit of experimenting around, but it's not too hard. At first, let's multiply both sides by cosine under the condition that's not equal to 0. Once again, you can go through the real life analysis to determine if it can be equal to 0 or not. But we're going to multiply by it on both sides, leaving us overall with, okay, here we got the sine times x minus m is equal to, now we are going to get negative the cosine squared divided by the sine times x plus the cosine squared divided by the sine times r minus m times the cosine of phi. Now we are going to solve everything for x, meaning we are going to add m on both sides plus m, and we are going to add cosine squared divided by sine times x on both sides, giving us overall, and also we are going to express the cosine squared as being 1 minus the sine squared for this part right here. We're going to get sine times x, then we're going to get plus. Now we're going to get 1 minus the sine squared divided by the sine times x is equal to, now we're going to get on this side cosine squared divided by the sine times r minus m, we can factor it out and we can make a plus out of it. If we were to factor out the m on both terms, 1 minus the cosine. Now what we are going to notice is if we were to factor out the x, okay, we are going to get sine plus 1 minus sine squared over sine. If we were to expand this sine by sine over sine, we are going to get sine squared over sine, meaning if we were to bring everything together, this is something times x. They both have the same denominator, meaning what we get in the numerator is sine squared plus 1 minus sine squared. You see, this is going to cancel out very nicely, divided by the sine. Meaning overall, on the left hand side, all that is basically left to get ourselves just x is multiplying by the sine, because we got 1 over sine as the coefficient of our x. And meaning overall, if we multiply both sides by the sine, we are going to get that x is nothing other than cosine squared divided by sine times sine. Sine and sine are going to cancel out times r, giving us just the cosine squared times r plus m times the sine times 1 minus the cosine. Didn't that turn out very nicely? I mean, that's a very nice simplification. That's way better than what we had at the beginning. Tons of cotangents and tangents. And now this right here is our xi, obviously. And now we need to find our yi. How can we do this? Well, by plugging our x value into either one of these functions. And I tend to go with g of x because it has less terms, so this is probably going to make our life a tad bit easier. Meaning if we evaluate our g at xi, what we are going to get is the tangent of phi. And as mentioned before, we are going to express it by the cosine and the sine. So sine divided by the cosine times our x, where our xi is going to be on the one hand cosine squared times r, and then plus tangent times m times sine, blah blah blah. So sine divided by cosine times m times sine times 1 minus the cosine. And all of this minus m times the cosine. Well, that's a mouthful, I would say, but we can do better than that. I mean, here, cosine squared and cosine is going to cancel out, meaning we are going to get sine times the cosine times r plus. Now you are going to notice that, well, we got sine squared on here, okay, on top. Meaning what we can basically do is we can turn the sine squared into 1 minus cosine squared. Meaning overall we are going to get two parts basically. On the one hand what we are going to get is 1 divided by cosine times m times 1 minus cosine. Then we are going to get the part with the negative cosine squared. Meaning negative cosine squared divided by cosine squared, and the cosine is going to cancel out, giving us just negative cosine times m times 1 minus cosine. And then we still have this part, minus m times the cosine. Now we can do a few more manipulations, obviously. What we are going to do is we are going to multiply things out a tiny little bit. Now I need to get an overview. It's not too easy to keep track of everything. Let us factor out the m at first. If we were to factor out the m at first, no, I did something wrong. We had m divided by the cosine of phi. I was already wondering why stuff was a tiny bit weird. M divided by the cosine, because I thought the simplification would be a bit easier, and it actually is. Because if we were to factor out m divided by the cosine on these two parts, we are going to get that is the sine times the cosine times r, then we are going to get plus m divided by the cosine. And then next up is that we are going to get in parentheses 1 minus the cosine, and then we get minus 1. Okay, this and that is going to cancel out, meaning we also have cosine cancelling out with this one, so we only are left with an m here, minus the cosine times m times 1 minus the cosine. Now these are our parts which are still left, and you see that we got an m here and we got an m here, meaning overall what we can do is we can factor out the m once again, plus, and now factoring out the m, we are going to get, putting the cosine into here is going to give us, and bringing the negative to the front, or we are going to drag the negative sign into here. That's a lot of algebraic manipulation, okay? So you need to be careful here. We are going to get the cosine squared in parentheses. Cosine times cosine is cosine squared. Then we get negative cosine. And we are also going to get, if we were to factor out a negative 1 here, negative 1, just simply. And this right here is going to be equal to the intersection y coordinate. And now what we are going to do is we are going to find the distance between our intersection point that we just now find out, and also our router bit. This is basically part 2 of part 2. Oh! For this next part you need to follow me really carefully. It's going to be a huge mess, which is going to simplify so fucking nicely you won't believe your eyes. Just like with Lagrangian mechanics, most of the times it's very Lagrangian-esque, to put it into nice words. So what is the distance exactly? If we have the distance in a plane, it's just going to be the Euclidean distance. What you can do is you can project a triangle into here, meaning it's once again just a slope triangle. The difference in y values and the difference in x values. This is going to give you your distance, or in other words the hypotenuse of this triangle. Meaning it's basically just our x and y coordinates in a difference, all of this squared, and then taking the square root of this. Just basically Papa Pythagoras to find yourself the hypotenuse. Meaning if you want to find the distance d between our point and also our xr, yr, what we need to do is we need to take the square root of the squares of the differences of the coordinates respectively. Meaning on the one hand the x coordinate of our point, okay, our router bit, is going to be r minus xi, and all of this squared plus, and next up we are going to get our our y coordinate of our router bit, namely negative m minus yi squared. Now what you're going to notice is that we can factor out a negative 1. Here negative 1 squared is going to give us just 1, meaning we can put a plus into the middle. And now we are going to compute everything one after another. Let's start with r minus xi, and once we got this we are going to square it. Same process here, and at the end we are going to see what the addition of these two are going to be, and then the corresponding square root. Now let us start with r minus xi. By using just the definitions that we got, we get r minus, this right here is our xi coordinate, so minus r times the cosine squared, I'm going to leave the phi out once again, plus m times the sine times 1 minus the cosine. Now you're going to notice that this first part, if we were to factor out an r, is going to be r times 1 minus the cosine squared, which is going to be the same as r times the sine squared. There's nothing else we can really do with this expression. I mean, it turned out a bit nicer than before. We got rid of one trigonometric term, you could say. And now we are going to square the whole thing. Meaning, and now once again, be very, very careful with everything. Okay, take a deep breath and try to understand what I'm doing here. If we square this, we are going to square the first part. So r minus xi squared. It's going to result in the binomial expansion of degree 2, namely r squared times sin to the 4th power. Next up, what we are going to get is both of these multiplied together with a factor of 2. So we are going to get a plus in the middle. So minus, I'm terribly sorry, since we have a negative sign here, negative, okay, so we are going to get a negative here. Please be careful, as mentioned before, really, really careful. So minus, since we have minus in the middle, 2 times r times m times, and now we are going to get sine squared times sine is going to be sine to the 3rd power times 1 minus the cosine. And squaring the last term is going to give us plus m squared sine squared 1 minus the cosine squared. That was easy. Let us continue with the second part, with the addition of the two y-coordinates or the difference of the two y-coordinates and then everything squared. So what about m plus yi? Well, this is going to be just m plus, and our y-coordinate of our intersection point is this one right here. So plus, I'm going to start with the m here, m times the cosine squared minus the cosine minus 1, and then plus r times the sine times the cosine. You're going to notice if we were to factor out the m here, we're going to get m times 1 plus the cosine squared minus the cosine minus 1. This and that is going to cancel out, giving us the cosine squared minus the cosine here, meaning if we were to factor this out too, we're going to get m times the cosine minus 1, and then plus r times the sine times the cosine. And we are going to go a step further and say that our addition of these two, m plus yr, is going to be r times the sine times the cosine, and now we are going to factor out the negative 1 here, meaning negative m times the cosine times 1 minus the cosine. I'm doing this on purpose because, lo and behold, we also got it of this form here too, 1 minus the cosine. Because now we need to square it, and don't forget, at the end we are going to add both the squares together and take the square root. Meaning if we were to square this now, m plus yi squared, we're going to get overall, okay, those two terms squared and then just multiplying those two together times a factor of 2, giving us overall r squared times the sine squared cosine squared. And then next up we are going to get minus 2 times r times m times the cosine squared, cosine and cosine, times the sine 1 minus the cosine, and last but not least we are going to get plus m squared cosine squared 1 minus the cosine, but all of this squared. Now, if we were to compare these two, this one, okay, our difference in y-coordinates, and also what we got down here, you're going to notice that they are pretty similar, with one exception. We got all the signs here, but in this expression we got a ton of cosines. But the cool thing is they are not simple cosines, they are cosine squares. And cosine squares are the same as 1 minus the sine squares. Meaning if we were to express each and every cosine squared with 1 minus the sine squared, we can start multiplying stuff out a bit more. Let us start with the 1 parts at first. We're going to get r squared times the sine squared. Now multiplying this by a sine squared too, but with a negative in the front. Negative r squared sine to the 4th power. Now we are going to continue this process. Negative 2 times r times m times, okay, cosine squared is going to go away. It's going to turn into 1 and then negative sine squared later. So times the sine times 1 minus the cosine. For the next part, we are going to have negative, and negative is going to become positive. 2 times r times m. Then we got sine squared times the sine is sine to the 3rd power times 1 minus the cosine. And last but not least, last summand, so plus m squared, and now we are going to get cosine squared, going to get rid of this, giving us 1 minus the cosine squared. And last part is negative m squared sine squared and then 1 minus the cosine squared. And what happens if we add those two together? Meaning, what is the addition of r minus xi squared and our m plus yi squared. Well, I tell you what it is. Let us compare our parts. Now, what you see here is negative r squared sine to the fourth power. You guessed it. We got r squared sine to the fourth power, but with a positive sign at the front. This one right here is going to die in a corner, as well as this one, giving us just the additive identity. Now, this part right here, do we recognize this in some way? I don't think so. We don't find this down here. But what about negative 2 times r times m sine to the third power 1 minus cosine? Oh, we got the same thing here, but with a positive sign. Hey, this is going to die somewhere in Mexico too. Now, what about last one? M squared sin squared 1 minus cosine squared. Oh, I tell you what, it's negative m squared sin squared 1 minus cosine squared. Also going to die somewhere. Hey, this is cool. So, meaning basically, all of the parts that we got in here in our difference of x coordinates are actually additive inverses to half of the parts that we got here on our difference of y coordinates. Meaning what we're going to be left with is just plain old r squared sin squared, oh, it's so nice, the simplification, minus 2 times r times m sine 1 minus the cosine, and then we're going to get plus m squared 1 minus the cosine squared. And well, there's not much more we actually need to do here, apart from one thing. You probably recognize it immediately, but what we got here is nothing other than a binomial expansion once again. This right here is the first part, namely r times the sine of phi, and then negative m times 1 minus the cosine. And all of this squared. I mean, we can do a bit better than that, dragging the negative sign into here. It's going to give us positive cosine of phi minus 1. And well, now the best thing about all of this is that if we want to find the distance function, we are going to take the square root of the whole thing. So by taking the square root of what we got here, you are going to notice that the square root and the squared is basically just going to cancel out. We also need a square here, meaning the distance between our router fence and also our router bit is going to be just the absolute value of r times the sine of phi plus m times cosine of phi minus 1. This simplification is seriously orgasmic. Don't you agree? This is fucking amazing. And the best thing is distances are defined positive, and on our certain intervals from 0 to pi over 2, you could say all of our sine and cosine is also going to turn out very nicely, not going to give us any contradictions at all, meaning the difference or the distance between those 2 points is just what we got right here. And now we are done with the hardest step, you could say. And the last thing to do is to basically just find out what the angle phi is going to be in terms of all the other variables that we got here. And we got a problem with that. That's why I made a bunch of prerequisite videos, because we got sine and cosine here. But how do you solve something like this for phi exclusively? Let's find out in part 3. Oh! Such a horrendous amount of work just to get out this little one. It's so fucking ridiculous. And when I first derived it, I couldn't believe my eyes. It's so Lagrangesque. Seriously. It's crazy. And I had to use Wolfram Alpha and the like to seriously check if this could be right. And it is. This right here is the distance function. And now what we want to do is we want to bring everything together into some phi with respect to all of the other variables that are going to be known ones. Now, what we're going to do is we're going to multiply m out at first. Okay, if we were to multiply everything out, we got m times the cosine of phi minus m, and now let's bring m to the other side, meaning we can express the addition of our basically distance between our fence and the router bit and our basically pivot point, okay, location, as being just the addition of two sine and cosine waves, namely r times the sine of phi plus m times the cosine of phi. And now this right here screams for the harmonic addition theorem. I have used it several times before on simplifying differential equations, proving theorems, integration, etc. Such a useful theorem, and you can find the link down there in the description. I'm not going to derive it once again. I derived it before, hence the prerequisite video. But what I can tell you now is that we can express always an addition of n many sine and cosine waves as just one big cosine wave or sine wave in the phase plane. Meaning d plus m is going to be equal to some new kind of amplitude, okay? Two sine and cosine waves added together are going to increase or decrease the amplitude in some kind of way in the phase space times, and we're going to go with the cosine branch of things. The cosine of our original angle phi plus some certain phase shift in our original angle. Okay, this is just going to be some kind of angular displacement. And this angular displacement is of the form of the inverse tension of negative, the thing in front of our sine, so r divided by m, the thing in front of our cosine. This right here is d plus m. And now it's an easy thing to solve for, well, you can say phi, for example. Or if you have a given angle phi, you can now subtract m on both sides to get yourself basically the distance, which is going to be traced out by your router fence and your router bit. Really depends, but we want to go for phi here. By the way, do you know what our eta is? Our eta right here, our new amplitude, is just going to be in the phase space, basically Papa Pythagoras. So our original amplitudes that we got here, basically just the hypotenuse of this. So square root of r squared plus m squared. Okay, just to make things a bit more clear. And well, now we can start manipulating this a bit more, and this is why I created another video. This is what absolutely broke me on the way back from Italy, and it was just an easy problem of bijectivity. What we're going to do at first is we're going to make use of the fact that the inverse tension is an odd function. Recently made a video on that too, meaning we can bring the negative sign to the front, and we are also going to make use of the fact that the cosine is an even function, meaning we can drag a negative one out, and the cosine of negative argument is just the cosine of the argument. This is going to get rid of the bijectivity problem, what I'm referring here to, hell of a time I had. Link down there in the description too, prerequisite video. Meaning we can rewrite d plus m as being nothing other than the square root of r squared plus m squared times the cosine of the inverse tangent of r divided by m minus our angle phi. And now we got rid of all the bijectivity problems, whatever the fuck, everything that could be a problem overall, and now we can start solving for the angle phi. It's as easy as this. We're going to divide both sides by r squared plus m squared, not equal to 0, it's a distance obviously. Meaning we are going to get d plus m divided by r squared plus m squared is equal to the cosine of the inverse tension of r divided by m minus phi. Now obviously, since we got rid of all the bijectivity problems by doing this little manipulation inside of the argument of the cosine, we're going to take the inverse cosine on both sides, giving us overall that the inverse tension of r divided by m minus phi is going to be equal to the inverse cosine of, well, what we got here, d plus m divided by the square root of r squared plus m squared. And the last thing left to do is to add phi on both sides and subtract our inverse cosine on both sides to get phi with respect to three variables, okay, which are changeable at all times. You can vary the distance between the router bit and the fence, you can change your pivot point, and you can also change how wide your router table is going to be. So we got phi with respect to d, r, and m being equal to the following wonderful thing, namely the inverse tension of r divided by m minus the inverse cosine of d plus m divided by square root of r squared plus m squared. And for the degree suckers, you can multiply everything by 180 divided by pi to get yourself the radians too. Or the degrees, I can't remember. Don't take my word for it, I don't care. But this right here is what we were striving for, okay? All of this work just to arrive at this very easy to remember expression for your angle phi. Now someone can create a spreadsheet and find out what phi can possibly be for certain values here, and then you can have a very nice and accurate router table. Boy. But yeah, this has been the problem, and I hope you did enjoy what you have seen today. Seriously, such a fucking ridiculous effort for something that I'm not going to use in a practical application. But it was so much fun to figure out, and this is what engineering should be about, and this is what mathematics is about. Taking a simple problem and making it complicated as fuck, because we fucking can. And I was so anxious to create this video because I was seriously anxious that I'm going to do a huge mistake in my derivation or something on the algebraic manipulations. But it turned out very nicely, apart from this one m times cosine instead of m times 1 over cosine. But whatever, I'm going to put an annotation into the video and then everything is going to be fine. But I hope you did enjoy this video. I had a lot of fun with this and it was a lot of fun to figure out. And maybe someone can seriously create a spreadsheet and just take a look at what fun needs to be such that you get a certain centimeter part out or whatever the hell. And other than that, thank you guys for watching. If you enjoyed this video, then definitely make sure to subscribe to the channel and to also subscribe to Flammy's Wood. Don't forget to check out stemage.eu, once again emphasizing that we got the cyber tensegrity going now. It's so beautiful. The smell of the olive wood, so good. And up until the next video, I'm wishing you guys a flammable fucking day. Please stay safe. Ciao.